I'm going to use the Laplace transform method to solve the second order ODE. Y prime prime plus 4y is equals to f of t, subject to the initial conditions. Y naught is equals to 0, y prime naught is equals to minus 1, where the f of t there is equals to 1 if t is greater than or equals to 2 and 0 otherwise. So we are given that a second order ODE. I usually find it convenient to sketch the graph of f of t. So for the graph of f of t, I will have my horizontal axis labeled a t, and then the vertical axis labeled the f of t, and then put a 0 there, and then put my point 2, and then the point 1, and then our function is 1 whenever t is greater than or equals to 2, so it's 1 there. And the next step is to write our f of t in terms of the Heaviside function. So in this case, we see that our f of t is equals to h of t minus 2. So that our differential equation becomes y prime prime plus 4y is equals to h of t minus 2, subject to the initial conditions. Y naught is equals to 0, y prime naught is equals to minus 1. So that's the equation that we now have. And the next step is now to take Laplace transforms on the differential equation there. So if we take Laplace transforms, what we would have is the Laplace transform of y prime prime plus 4 multiplied by the Laplace transform of y is equals to the Laplace transform of h of t minus 2. And for the Laplace transforms, we get them from the table. For the Laplace transform of y prime prime is s squared y minus s times y naught minus y prime naught. For the Laplace transform of lowercase y, we denote it by uppercase y. For the Laplace transform of h of t minus c, it's exponent of minus cs divided by s. And then we substitute the expressions that we have obtained from the table. So therefore, the Laplace transform of y is s squared y minus s times y naught minus y prime naught. Then for the Laplace transform of y, it's an uppercase y, so we have plus 4y. And then on the right-hand side, we are having h of t minus 2. So by comparison with this one, we see that our c is a 2. So that when we substitute c equals to 2 here, we will get our right-hand side is exponent of minus 2 times s over s. And then I can just rewrite this part here as exponent of minus 2s, so that we have on the right-hand side the exponent of minus 2s divided by s. So and that's the equation that we have. Then we go on and look at these initial conditions that we are given. We substitute them here so that our equation becomes s squared y minus s times 0 minus minus 1 plus 4y is equals to exponent of minus 2s. And then the s times 0 there gives us a 0, so that our expression becomes s squared y plus 1 plus 4y is equals to exponent of minus 2s and divided by s. And then combine terms and factor, then we would have y multiplied by s squared plus 4 plus 1 is equals to exponent of minus 2s and divided by s. And the next step is to make y subject of the formula. We put the 1 on the right hand side, then divide by s squared plus 4, so that our expression becomes exponent of minus 2s divided by s times s squared plus 4 minus 1 divided by s squared plus 4. So that's the expression that we have there now. I can just factor out this exponent of minus 2s, so that we have y is equals to exponent of minus 2s multiplied by 1 divided by s multiplied by s squared plus 4, then minus 1 divided by s squared plus 4. But if we look at this expression here, we don't have any f of s of this form. So we have to rewrite it using partial fractions. So and we would get 1 divided by s multiplied by s squared plus 4 is equals to a divided by s plus bs plus c divided by s squared plus 4. And when we solve for a, b, and c, what we would get there is it's equal to 1 divided by 4s minus s divided by 4 times s squared plus 4. So what you have there is our y is equals to exponent of minus 2s multiplied by 1 over 4s minus s divided by 4 over s squared plus 4, then minus 1 over s squared plus 4. So that's the expression that we have. For us to find the solution of the ODE, we take inverse Laplace transforms, so that we have our y of t is equals to the inverse Laplace transform of the y that we just written here. So that's our solution there for the y of t is the inverse Laplace transform. So we then go on and take those Laplace transforms. I'll go on and look at each part separately. So we'd have 1 over 4 multiplied by the inverse Laplace transform of exponent of minus 2s divided by s, and then minus 1 over 4 multiplied by the inverse Laplace transform of exponent of minus 2s multiplied by s divided by s squared plus 4, and then minus the inverse Laplace transform of 1 divided by s squared plus 4. And then go on and look at this part here, the inverse Laplace transform of exponent of minus 2s divided by s. From the table of Laplace transforms, we see that that is equivalent to the Laplace transform of h of t minus c. So by comparison of this part here and this one, we see that our c is equals to 2. So we then go on and substitute c equals to 2 here, and we would get that the inverse Laplace transform of exponent of minus 2s over s is equals to h of t minus 2. But here we are having a 1 over 4, so that would have 1 over 4 multiplied by the inverse Laplace transform of exponent of minus 2s over s is equals to 1 over 4 multiplied by h of t minus 2. So I'll go on and put this expression into our equation here, and then move on to the next part, and this one here. So I'll go on and look at the inverse Laplace transform there of exponent of minus 2s times s divided by s squared plus 4. From the table of Laplace transforms, we see that this inverse Laplace transform is equivalent to the inverse Laplace transform of h of t minus c multiplied by f of t minus c, just because we are having an exponent of minus cs multiplied by a Laplace transform. So in this case, we see what is multiplying the exponent there is s divided by s squared plus 4. So that is our f of s there is equals to s divided by s squared plus 4. But this f of s, we see that it's similar to the Laplace transform of cosine of at. But for cosine of at, we are having an a squared there, so we have to rewrite this 4 here, and it will be rewritten as 2 squared. So our expression will be s divided by s squared plus 2 squared. Then by comparison of these two parts, we see that our a there is equals to 2. So if a there is equals to 2, from our table of Laplace transforms, for the cosine of at, substitute a equals to 2, it will give us our f of t there is cosine of 2t. Now that we have obtained our f of t, we then go on and look at the c there. So for the c from this part here, we see that our c there is equals to 2. So if c is equals to 2, when we substitute into this expression where we are having f of t minus c, we are saying f of t minus 2, substitute it here. Wherever we are having t, we put t minus 2. So we have f of t minus 2 is equals to cosine of 2 times t minus 2. And from our table here, the inverse Laplace transform of exponent of minus cs times f of s is h of t minus c multiplied by f of t minus c. And we have obtained the h of t minus c and the f of t minus c, so that our inverse Laplace transform of 1 over 4 multiplied by exponent of minus 2s times s divided by s squared plus 4, it will then give us 1 over 4 h of t minus 2 multiplied by cosine of 2 times t minus 2. So I will write the expression in our equation here. It's a minus 1 over 4. Then go on and look at this part here, the inverse Laplace transform of 1 over s squared plus 4. So for that inverse Laplace transform, from our table of Laplace transforms, we see that it is similar to the Laplace transform of sine of at. So we are having there our f of s is 1 over s squared plus 4. But for sine of at, we have this a squared. So we'd have to rewrite this 4 as a square, so it would be a 2 squared. But if we have an a there, then we should have an a in the numerator, of which we are saying our a will be a 2 there. So we should introduce a 2 in the numerator so that our expression becomes a half multiplied by 2 and divided by s squared plus 2 squared. Then we will see that our a there is a 2. So a equals to 2. Then from our f of t, which we are saying is the sine t, it is the one that gives us the inverse Laplace transform of 1 over s squared plus 4. Then it will give us a 1 over 2, then multiplied by sine of 2t. And I will put that in our equation there. Then if we look at these parts here, we have the 1 over 4h of t minus 2 is common, so I can just factor it out. Then we have 1 over 4h of t minus 2 multiplied by 1 minus cosine of 2 times t minus 2, then minus a half times sine of 2t. So that's the solution there.